We were talking about a very useful method, namely substitution for indefinite integral. Now, let me discuss this for the definite integral. For the indefinite integral, if we have some expression like that, with the integration variable t, we can use substitution, namely t is 5x, some function, and we can rewrite the integral into this form, which may be easy to integrate. And now, what if we have the limits? What if we have the definite integral, say from alpha to beta? This alpha means that x starts at alpha and runs up to x is beta. We can't write the same limits alpha beta here, because this value gives the starting value for t, which is not necessarily the same as alpha. In general, it may be some two numbers which are related by this function. If x starts at alpha, then t is phi of alpha. And this is the starting value for t, which we denote a. And the endpoint, the final value for x is beta. And when x goes up to beta, then t goes up to b, which is phi of beta. Well, written in this form is pretty difficult to understand, at least for the beginners. Let me compute a few examples that will make things very simple, very clear. And similarly as before, for the by parts method, we have again two ways, two possibilities. Either we can use substitution to find the antiderivative and then evaluate the antiderivative in the x limits, or we can use substitution to convert this definite integral into this definite integral, and then we use the t, the new variable, limits. Let me illustrate both ways by the following example. Consider the integral from e to e squared of the function logarithm square of x divided by x dx. You can see that logarithm might be a good suggestion for the substitution. So let's write t is logarithm of x. This is a particular case for this general writing. T is some function phi of x. Here phi is the logarithm. And then we must recompute the differential. dx and dt are not the same. Dx multiplied by phi is dt. And if phi is logarithm, then phi derivative is 1 over x, the derivative of logarithm, dx. So, yeah, let me show this in color. Phi derivative dx is this expression now, and this is dt. And when we compute the definite integral using substitution, we must recompute three things: the function, the differential, and the limits. There are two limits, so actually four things, right? If x starts at e, then t starts at logarithm of e, which is 1. 1 is now a, which was here. And when x goes up to e squared, then t goes up to logarithm of e squared, which is 2. And this is the b, namely phi of beta, where beta is e squared. Then what about the function? Then dx divided by x, well, yeah, that should be yellow. This is the differential, and we have logarithm square of x. Logarithm is t, so we have t squared. And t square integral is t cubed third. From t is 1 to t is 2. Well, and we evaluate the antiderivative at these new limits and subtract. So we have 2 cubed third minus 1 cubed third, which is 8 minus 1, which is 7 third. So once again, when we compute a definite integral using substitution, we must recompute the limits, the integrated function, and the differential. And this is the result. Well, as an alternative approach, we can forget the limits and we can compute the indefinite integral first, and only then use the limits of x. Let me show this, and let me stress the advantage and disadvantage of this second approach. So the alternative is like that. First we compute the indefinite integral, that means no limits, just a function, logarithm square of x divided by x dx. We use again the same substitution, t is logarithm of x. So dt is dx divided by x. And we have logarithm square is t squared. Dx divided by x is dt, which is t cubed third, possibly plus c. So we see no limit here, no limit here. So we don't have to recompute the limits. This is the advantage. But the disadvantage of this second alternative is that we must go back from the new variable t to the old variable x if we don't want to recompute the limits. So, one more step here, t is logarithm of x, so logarithm cube of x third plus c. And now we can write the definite integral from e to e squared of logarithm square of x divided by x dx is square bracket, and we write the antiderivative logarithm cube of x third from e to e squared. You see, in this second alternative we don't have to recompute the limits, but we must go back from t to x. And then we have the antiderivative in x, and we substitute the limits for x, and we subtract. So that would be logarithm cube e squared third minus logarithm cube e third. But logarithm of e squared is 2, 2 cubed is 8. And logarithm of e is 1, 1 cubed is 1. And 8 minus 1 is 7 third. Yes, the same result. I would say that in most cases the first version, when we recompute the limits and don't have to go back to x, is a better way. A little shorter, a little faster, a little quicker, a little easier. Actually, I said we don't have to recompute limits. This is not absolutely true. You see, how did you get this 2? By substituting e squared to logarithm. But if you observe this carefully, we did the same computation even in the second alternative. E squared evaluated for logarithm, right? Or logarithm evaluated at e squared. So we did the same computation. It's not a big help. I prefer the first way, but both are possible and you can choose your own, you can choose your favorite way.